Good morning to all. We are going to discuss trees and binary search tree concept in programming and data structures. So before going to discuss a tree and binary search tree, we are going to discuss what is the meaning of data structure. So data structure, we know that it is a specialized format in order to store and after that process based on the conditions we have provided. And also we want to retrieving the data. So where actually it is stored. So it is a specialized format of storing, processing and retrieving data. So generally, data structures can be classified into two types. That is, that a linear data structure and a non-linear data structure. So, what are the terms comes under that linear data structure, such as arrays, stack, queue, linked list. Okay, then non-linear data structures, trees, graphs. Okay, so why it is called a linear and non-linear? So linear, nothing but the data are arranged in the form of sequential format. So we know that the exact location where actual data is available. But in the case of non-linear, that is the data are stored in the form of hierarchical manner. So that's why it is called a non-linear. That is a major difference between a linear and non-linear. If the data are available in the sequential form, then we can say that the linear. Otherwise, if it is the form of hierarchical, then we can say that non-linear data. So the why so we suppose if you have a yeah, applications are based on that non-linear, then we can go for trees and graph. So if you want to develop any applications the based on the sequential, so for example the student data you want to store, then we can go for the concept of arrays. So based on the application the customers need, then we can select that appropriate data structure. Not compulsory you have to use a trees or not compulsory you have to use arrays. So it is not like that. The based on the customers availability or the what application we want to develop, so according to that we can choose our data structure, linear or non-linear. Okay, then what is the importance? So why we want to select the data structure? So nowadays most of the companies peoples are looking the students are very clever with the data structure. So why? So we can able to develop the concept. So what concept you want to develop in your current application, that is very important. And after that you have to write the algorithms, nothing but what the step by step, that is some I mean a written format, step by step we can explain our concept. And then not the mission never understand the I mean the theoretical explanation. So as a human we should understand what is the algorithm. Suppose we want to add two numbers a and b, we want to add, so what we are going to write. So get the a value from the user, whether the a is the data about what kind of the data, maybe the integer or the characters, or what kind of data, that is the type of data you want to add, either if you want to add with a string or integer or float, anything. So you just write it in the theoretical form. But how the machine can understand our algorithm, it is not at all possible. We go for any programming language, maybe c or c++ or java, or if you want to use any scripting part, validation things you want to include in your concept or in your application, then we can go for some languages. So we can go, so you have a concept, then after that we are describing your concept in the form of algorithm. Then after that what to do, we want to implement in your programming language, then only the machine can understand. We can go for any programming languages. So this is the concept of tree. So the tree is what? It's a nonlinear data structure. So here, this is a tree format. So we can start. So already we know that it's a nonlinear data structure in the form of hierarchical. The data are arranged in the form of hierarchical. Here we have a root node, then followed by we have a parent node. Then the next two nodes are the children's, that is a child nodes, the last nodes are leaf nodes. So leaf nodes nothing but what's no more nodes are available. So here you see, so this is a root node, the starting node is called the root node. Then after that we have a parent node. So the first level is called level 0. You can start from the level 0, the level 0 which indicates that what the root node. Then we can next level 1, that is a parent node. Then the third is what, level number 2, and so on. So these are all the important terms or terminologies available in a tree data structure. The first one is what, parent node, the node which is a predecessor of your node, and then child node, the node which is the immediate success of your node. Then root node, that is a starting node, or we can say that the top node of your tree, are the nodes which doesn't have any parent node, because it is a starting node. So starting node never have any parent node. Then the degree, so the degree of a node, nothing but the total count of subtrees attached to that node. Okay, that is excluded your parent node. Then we have a leaf nodes or external nodes. The nodes which don't have any child nodes are called the leaf nodes. So we generally, if you take any tree format in the data structure node, the last level, that is the nth level, whatever nodes are available in the nth level, those nodes are called as a leaf node. So why? Because we have no more nodes available from that leaf node. Then we have a ancestor of your node, any predecessor nodes on the path of your root to the node. From the root node to a leaf node, what is it? The directions go from left to, then right to left, likewise till the leaf node. Then the descendant, any successor node on the path from leaf node to that node. Then we have a sibling, then children of the same parent node, they are called siblings. Then the depth, the count of edges from root to node. Then height of the node, the number of edges on the longest path from the node to be a leaf. Then this is a very simple example. You consider this is a tree. So here you see that is A is a root node or the topmost node. Then it has two nodes, that is a B and C. Actually, what, B is a parent of D and E. B is a parent of D and E. Likewise, C is a parent of F and G. So here we have a siblings. D and E are the siblings, siblings of the B node. And then the leaf nodes we consider D, E, and F, G are the leaf nodes. So these are all the types of the tree data structures. We know that the general tree, nothing, we don't have any restrictions. We can able to include n number of nodes. Okay, it means that the parent node can have any number of child nodes, maybe 2 or 3 likewise. But in the case of binary tree, so binary tree know that, so we have a condition that is a maximum number of 2 child nodes. Okay, we have a 0 node, 1 node, or 2 nodes. That is at most maximum 2 child nodes. If it is exceed this condition, then it is called as a general tree. Suppose we have A is a root node. That node consists of some B, C, D. These are the child nodes. So what will happen? It is not the binary tree. So binary tree nothing but can have a maximum number of 2 child nodes. Then we have a balanced tree. So balanced tree nothing but the height of the left subtree and the right subtree are equal or differs at most by 1. Okay, then it is called as a balanced tree. Then we have a very important, that is a binary search tree. So in that binary search tree, it is also similar to binary tree, but we have some condition. So what is the condition? No, the left side of that is a left hand side of the tree node value should be less than of the root node, and the root node value should be lesser than of the right side node. Okay, so that is a condition. So as a name implies, binary search trees are used for various searching and sorting algorithms. So the examples include AVL tree and red black tree. It is also non-linear data structure. It shows that the value of the left node is less than its parent, while the value of the right node is greater than its parent. So this is the condition. So it is a very important condition. Based on the condition only we can able to solve the problems. Okay. So now we can move on to the binary search tree. So binary search tree is a node based on the binary tree. So it is a basically binary tree. So binary tree nothing but what's at most two child nodes. So that is a basic condition, and also it's following the following properties, that is a left subtree of a node contains only nodes with the keys lesser than the root key value. What is the meaning of that? So whatever left side value, left subtree values are available, those values should be lesser than of your root node value. So likewise, the right side subtree of a node contains only nodes with the keys that is a greater than of your root key. Suppose the left hand side I have a 2, then the root node value is what? 4. Yes, the 2 is lesser than of 4. Correct. Suppose the right side value I have a 8. Yes, the 8 is a greater than of the 4. So the condition to the properties satisfied. Properties of binary search tree is satisfied. So we can go for it's a correct binary search tree. Then this is an example of binary search tree. So here you see the root node value 8. Now just to come to the left hand side, here we have a 3. Yes, 3 is lesser than of 8. Then again here come here, that is what is the meaning of that? The root node value here 8. Okay, the left hand side value you see here 1, 3, 6, 4, 7. So all values are lesser than of 8. Condition true. Now you just come to the left hand side and also again apply the same rule again and again, then you can check the condition. So here this is a root node 3. Yes, the 1 is a lesser than of 3. Condition true. Then come to here the 6. 6 is a greater than of 3. Condition true. Again come here, come down the 4. 4 is a lesser than of 6. Yes. So 7 is a greater than of 6. So the properties are satisfied in the left hand side. So likewise come to the right hand side. So here you see 10, 4, 10, 14, 13. So these are all the values are greater than of 8. Condition true. Then again come to the right subtree. So here you see 10. Yes. So the left hand side of 10 is nothing is there. Then come to the right hand side 14. Yes, 14 is a greater than of 10. Condition 2. Then come to here that 13 is a lesser than of 14. Yes, the condition satisfied. The properties are satisfied. Then we can say that it is a purely binary search tree.
So the second slide, we can easily understand. Here you see, first we'll see the right side picture, which shows that we have a root node, the root node, that element E. Then the left side values are, you see, that here represented in the form of labels. Here we have the next level C and then H. We have two child nodes. Then we have a level number 3 AD, which belongs to C, and then F and I nodes are belongs to H. Likewise, we have a B node, that is a child node of A. So this is the way we have to represent the labels. Okay, but in the form of values, how we can select the values, how we can insert the value at the corresponding node. With the help of the previous properties, we have to remember that previous property. With the help of that, we have to check it whether it satisfies a condition or not. Once it is the condition satisfied, then it is called as a binary search tree. Okay, now come on, we can. Okay, fine. The left side here you see 3. So left subtree is what? 3. So the 3 is a lesser than of 8. Condition true. Likewise, you see the right side value 10. So 10 is the maximum when you compare with the root node. First level satisfied. Now come to the second level. Here you see 1. 1 is a lesser than of 3. Okay. Now come to the right side 6. 6 is the maximum of 3. At the same time, we have to compare with the root node also. It is a, so whatever values are available in the left side value, all values should be lesser than of our root node value. Okay. So here also it satisfies our condition. Now come to the next part 14. So the 14 is a node which is available in the right or not. Okay, now we'll see. So by where is the smallest element? Actually, if you are take any I mean binary search tree, we have to check it whether which one is the very lowest value. So the lowest value here, what's left to most element. So usually the left to most element which is the smallest value. So likewise, where is the largest element that should be available in the rightmost. You see the example in the previous one. So here the minimum is what 1 and then maximum is what 13. So 13 is presented at the thing. So we have a one tree format is there in the, I mean, which satisfy our properties of binary search tree. Now we want to find out any values. That values whether it's available or whatever thing you want, whatever value or whatever element you want to search on the binary tree, we have to make sure that whether the tree is satisfied our condition or not. That is a first step. When the condition satisfied, then we can start our searching process. Okay, now we'll see how to do that. So start at the root node. First step, we have to start at the root node. Now compare the value of whatever item or whatever element or whatever value you want to search, that should be compared with the root node. If it is matched, for example, in our here E, okay, suppose we want to find out whether it is our searching element is, it's an example I'm saying. So our searching element is E. Otherwise, right side value, whether that whatever value find out whether it is available in the right side or not. So this is a procedure we have to found. We have to check it whether our I mean our searching value or element which is available or not.
Okay, now we want to check. So suppose a particular values are available on the tree or not. So how to check it? So this is the algorithm. So initially we have to check it if the root node value is equal and null. Nothing is there. So if you have a root node value, then only we have a tree. So for initially you have to check it if root is equal and null, then root hyphen key is equal to key. Okay, then the return the value is what root. Okay, key is a we want to find whether that is available or not. So for initially we are going to check whether the root is equivalent to null, then the root of key is equivalent to key, then we can return that is a root node. Otherwise, what to do with the help of key, key is a greater than of root key, what to do? We can go for the right hand side. Okay, when the root of key, then if it is a less than key, then we can go, move on to the right hand side, then we can check it whether it is available or not. So it's a very simple, you can check it with, initially we can check it with the root value. If it is a equal that you are searching value, then you can return it. Otherwise, what to do? If it is a greater than of root key, suppose our key finding is what 4, our root node value is what 8. So what to do? We can go for the left hand side. Why? Our key value is a less than of your root node value. If it is a greater than, then we can go for the right hand side. So only we have a 3 condition. Okay, so now that is a very simple. We want to check. We want to check or we want to search the given the tree whether the 6 is available or not. So 6 is what our searching key, searching value, or we can say that the searching key. Now we want to check whether the 6 is available on the given the binary search tree or not. So how to check it? So what to do? So initially we can start from the root node. We can compare whatever the searching value, that is a 6. Now we can compare with the 6 with the 8. Okay, it is not equal. 6 is not equivalent to 8. Yes. So now what to do? The 6 is what? Lesser than of 8. 6 is what? Lesser than of 8. So we can directly go to the left hand side. You should not go to the right hand side. Okay, because 6 is a less than of 8, so 6 is a less than means what? We can go for the left hand side. Now we can start our searching process on the left hand side alone. Okay, so don't go to the right hand side. So now what to do? Come to the left hand side, again check it. Again check it, the 6 is equal to 3. No. Okay, the 6, what is that? 3 is our left hand side value, that is the 3 is a lesser than of 6. So we can go for the right hand side of your left subtree. So what to do here? The 6 is available, so that our searching value, our searching value of key which is available in the left subtree of the binary search tree. So once it is formed, we can return true. Otherwise, what to do? If it is not equivalent to a root value, it is not available in the left hand side, and also it is not available in the right hand side, then we can say that false. The same thing. So before we have concentrated how to finding the value. Okay, how to search or finding the value on the binary search tree, whether it is available or not, like that. So now we want to insert the value. So here a new key, if you want to insert, so we can start from the leaf node only. Okay, that is a condition. A new key is always inserted at the leaf node. You have a binary search tree, existing binary tree is available. Suppose you think we want to add one more value. So what to do? We can start from the leaf node. So leaf node, nothing but what? At the end of that is a level number n, nth level of your binary search tree. So we can go to the nth level, that is the last level. We can say the leaf node. We can go to the leaf node. Then we can start to insert the value. So after inserting, we can check the condition. What is the condition? Left hand side value. So those values are available in the left hand side. That should be lesser than of your root node. So likewise, the right hand side value should be greater than of your root node. That is a condition. So each and every time you have to check the condition. So okay, let's see one example. Okay, suppose we want to insert the 40. So what to do? We can start from the leaf node. So here this is a leaf node. So here we have a root node is what? 100, 20, 10. Then we have a then followed by 10, 20. So okay, here we have a 200. Okay. So now we want to insert the 40. So we can go to that. After that, I mean the right hand side of the 20 is what we have a 30. Then here you have to insert. And also check the condition whether it's true or not. That is what the left hand side value should be lesser than of the root node. So likewise, the right hand side value should be greater than of your root node. If it is satisfied, then it is correct. So we have one question. Suppose a number 751836094 So these are all the sequence. Some numbers are given or inserted in that order into the initially empty binary search tree. So the binary search tree uses a usual ordering on natural numbers. So what is the in order travels a sequence of the resultant tree. So as you know that the in order travels of the sequence of the resultant tree nothing but what should be in the form of ascending order. Okay, so the answer is what? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So the second question. So which of the following traversal outputs of the data in sorted order in a binary search tree? Simple, it is the in order. The post order, the third question, the post order traversal of a binary tree. So given the in order travels of the same tree is given. The height of the tree is the length of the longest path from the root to any leaf. So what to do? We can draw, we can make it as a diagram. So we can start from the 8 and then each and every day you check the condition. So we'll get the 6 and 9. Then the next level is what? 4, 7, 2, 5. So likewise, we can get it the one diagram. So from the diagram, you just count it that height of the trees. Actually, the answer is what? 4. So here we given the post order sequence are given and in order. So we have to construct the binary tree from post order and in order traversal. So what to do? We can start from that. So we can start from the sequence values 1. Okay, then we have a 2. So 2 is a lesser, we can insert the left hand side. The 3 is a greater than of that. So we can go to the right hand side. Then we have a 4 and 5. So 4 is a lesser than of 2. The 5 is a greater than of 2. So likewise we can insert. So finally we can get the diagram likewise. Then one more, if you remove the root node, which of the node from the left subtree will be the new root? So generally, if you want to cut the root node, so what will happen? So the leaf node value, so whatever leaf node value are available, which is written back to our root node. Again, the same procedure, you have to apply the binary search tree. So actually what will happen in the previous slide, suppose if you want to remove the root node. So root node here is what? 24 node. So after removing the root node of 24, what will happen? The leaf node value 16 will come back. Then again you have to apply the binary search tree format. Then we can get the result likewise. So each and every time check the condition. The left hand side value should be lesser than of your root node. Likewise, the right hand side value should be greater than of our root node. The same procedure again and again apply. While inserting the elements in the empty binary search tree, the sequence shown, the element in the lowest level. So you'll be get the answer is what? 69. So how? We can see one by one. So actually our tree is what? We can start from the empty tree. So here the empty tree is what? So we can start from the null tree. Then initially here given is what? 71, 65, 84, 69, 67 and 83. So now what to do? We want, this is some numbers are given. So actually our aim is what? We want to make it as a tree. We want to make it as a tree. So the initial value given 71. So what to do? We can start from empty. Then we have an initial value is what? 71. So now the 71 as a root node. Okay, then the next value is what? 65. So each and every time you have to compare with the root node whether the condition is satisfied or not. So what to do? 65. Next value is what? 65. So now you just compare it. So 65 is what? 65 is a lesser than of 71. So sure, we that value should be coming under the 71. That is the left hand side of your 71. So the 65 is a lesser than of 71. So you just make it as a left hand side. So now our second step, Over the third step, we want to insert 84. So now compare with the root node. So 71 is what? The 84 is greater than of your 71. So what to do? So we can insert at the right hand side. So now the diagram, we have a 71 is a root node. The next level, that is a level 0, we got it 71. At level number 1, we got it 65 and 84. Okay, so the totally three values are we have inserted on the tree. Now we got it at level number 1. So now what to do? The next value is what? 69. The same procedure. The 69 is what compared with the 71. So the 69 is a greater than of. Yes, 69 is a lesser than of 71. So we have to make it as the right hand side. So now here come back. But here you see one level, that is a level number 1 of the left hand side is what? 65. So actually the 69 is what? Greater than of 65. So you just make it in your right hand side of your 65. Okay, so the diagram will be like that. Next is what? 67. So now again you just to compare it. 67 is what? Lesser than of 71. So definitely we come to the left hand side. So the 67 again compare with the 65 here. So already we have a 69. So the 67 should be lesser than of your 69. So you just to make it as a level number 0, 1 and then to third level. Next we have a 83. So the 71 compare with the 83. So 83 is what? Greater than of 71. Okay, so definitely that value should be in the right hand side. So you just make it as a come to the right hand side. In the right hand side we have a value 84. Under that 84 you just make it as a left hand side of your 84 is what? 83. Okay, so this is a final output of actually the numbers given 71, 65, 84, 69, 67 and 83. So this is a diagrammatic representation of these numbers. Then one more example, it is also very simple. Let us insert the elements into the binary search tree in the sequence. The sequence are given, that is 50, 12, 62, 5, 2, sorry, 520, 58, 91, 3, 8, 37, 60, 24. Okay, so now the same procedure. So what we have discussed in the previous example. So we can start from the 50. Okay, so initial making the diagram node, that is a root node. So we don't have any condition, directly we can make it as a root node, whatever values are available. That is a level number 0. Then come to the level number 1. So here you see 12. So 12 is what? 12 is a lesser than of 50. So the 12 is inserted as a left child of 50. So our diagram will be what? 12 then 50. So this is what? Level number when you are inserting when you are insert the 12. Okay, then come to the third value. So third is what? 62. Now we want to insert the 62. Again you just compare with the root node. 62 is what? Is a greater than of 50. So definitely the 62 should be placed at the right hand side of your 50. That is a root node value. So the diagram will be like that. Next is what? So far we have a completed 50, 12 and then 65, isn't it? Now we have a fourth element is what? 5. So now we just compare with the root node. 5 is lesser than of 50. So 12 is checked with a 15. Again 5 is a less than 12. So 5 is inserted as a left child of 12. Okay. Next we have another next element is what? 20. So the 20 is a lesser than of 50. Root node value. When you compare with the root node, the 20 is a lesser. So definitely we'll go to the left hand side. So the 12 is checked with a 20, but 20 is what? The greater than of 12. So once the value compared with the root node, whether it's a lesser or greater, lesser means go to the left hand side. But in the left hand side also, again you have to apply the binary search tree. Okay, that is a recursive process only. So here you see, actually it is a recursive process. What is happening here? The 12 is great. 12, I mean, it's 20 is a less than 12, like 50. Okay, fine. So you go to the left hand side. So 12 is checked with a 20, but 20 is what? Greater than of 12. So 20 is inserted as a right child of your 12. So far we have completed 20. Next one is what? 58. So compare with a 58. So 58 is what? Greater than of 50. So what to do? So 62 is compare with a 58. So 58 is what? Lesser than of 62. So you can do the we can do the again changing the diagram. So the final diagram will be like that. So the next one is what? 91. So here we have 50. So 50 is what? That is a lesser than of 91. So we can go to the right hand side. You just do that insert. After that, that is the right child of your 62 is what? 91. Then we have a 3. So 3 is a lesser than of 50. So directly we can go to the left hand side and the leaf node value, that is a 5. 5 is a leaf node. So the next of the 5, you have to insert the 3. The same procedure repeated again and again till all the values completed, distributed on the hierarchical manner, that is in the tree format. Then we can stop the process. So till final value is given here 24. So once you have inserted the 24 on the given the binary search tree, and also check the condition, each and every time you have to check the condition. So once the condition is over and also all the values are distributed over the binary search tree, then we can stop the process. So the final output will be like that. Okay, so here given some codes. So what will be the output? So here I have taken one simple example. That is a B problem. So here you see the for loop given for I equal to 0, I less than 10, then I value incrementer, then print of percentage D, then I ampersand 1. Actually, I ampersand 1, nothing but what? We are going to performing that binary operation. So what to do here? So I values initially is what? I value is equivalent to 0. So every time we are going to do the increment process till less than 10. So what will happen? I values started from 0. It will goes up to what? 9. So less than 10. Here condition is what? Less than 10. No. So what will happen? I is equivalent to 0 to I value is equivalent to 9. That is a till 9. So we have to do the process. So okay, example, let I equal to 0. What will happen? Initially it is going to convert in the form of binary. So here we have a 0. No, binary value of 0 in form in the format of 8 bits. So what will happen? 40, then 40. Totally we have a 8 bits. So what we are going to do, after converting in the form of binary, we have to do the AND operation. Okay, that is a binary addition, binary calculations here. So here given that ampersand. So ampersand symbol is nothing but what? AND operation when the both the bits are, that is a left hand side whatever value as well as the right hand side. So the two inputs are the same. Okay, that is a 1 and 1. We can return the result is what? True. Otherwise 0. The same procedure here applied. So after converting the 0, that is 0 decimal to binary, we can get the result likewise. So now we have ampersand 1. So we can take the first bit of the binary is here what? 0. So 0 ampersand 1, the result will become what? 0. So likewise I value incremented, also already we have a 0. So once I value incremented by 1, now I is equivalent to 1. Again convert to a binary. So 1 ampersand 1. So both bits are same. Both the bits are same. Then we can get the result is what? 1. Then I is equivalent to the binary value of 2 is what? In the form of 8 bits, 4 zeros and 0010. So here the last bit is 0. So 0 ampersand 1 is equivalent to 0. The same procedure till we have to apply on when I value is equivalent to 9. So here you see 0, 1, 0, 1. So it will be repeated 0, 1, 0, 1. Okay. The same procedure will be applied till when I value is equivalent to 9. So here one more example. If tree 1 and tree 2 are the trees indicated below. Okay, so what to do? Which travels of the tree 1, tree 1 and tree 2 respectively will produce the same sequence. So here, so already we know that the in order, pre-order, post-order. So in order, nothing but what? So the root value should be presented in between the left and right. So pre-order, nothing but what? First root, then followed by left and right. Then post order, nothing but what? Left, right, then followed by a root node. The same procedure here you have to apply. So in the tree 1, so when you are applying the pre-order procedure, pre-order nothing but what? So first you have to visit the root node and then go for left, then followed by right. So when you are applying the rule on this tree, then we can get the result is what? A, B, D, E, G, H, I, J, F, C. Okay, when you are applying the in order procedure on the tree number 1, in order nothing but what? First visit the left hand side, then we can go for the root, at last visit the right node. So when you are applying the in order procedure on the tree, then we can get the result is likewise, that is a B, E, H, then I, J, A, F, A, C. Then likewise a post order nothing but what? So first visit the left hand side and then right, finally root node. So we can get the result likewise. Okay. So here the same procedure, same methods, that is the in order, pre-order, post order, you just applied here. So finally we can get the, what is the result? Will produce the same sequence. So here which one produce the same sequence? So here you see. So the post order and pre-order. Okay, so here you see G, J, I, H, E, F, D, B, C, A. Here also we got it in that in order. So post order in order, that both the sequence we got the result is what? Same. Okay, here you see in the tree number 1, we applied the three rules, that is the in order, pre-order, 3 traversals we have applied. So from that we can get the result likewise. So likewise the same procedure applied on the tree 2, we can get the result. 3 results we got it. From the 2 results, which are the results? The same sequence. Okay, that is actual they are asking. So that a result is what? In the tree number 1, we got it the post order sequence, and also in tree 2 we got the sequence in the form of in order. So both are same. Okay, post order, in order. So post order, in order. So the answer is what? C. So up to this, we have discussed some basics of trees and binary search tree. So if you have any doubts, you can clarify with me. Thank you, students.